Welcome to Advanced Reverse Engineering. There's homework. Looks like most of you did fine with it. It was to use Capstone and Python to do some disassembly. And you should have gotten something that looks just like this. You could use that or not. You should do it with IPython, and there was some things you can include. Let me go over my solution to this, because maybe it will be instructive. I won't do this every time. I think it's worth doing it this particular time, just because this is a whole lot of stuff. And so let's go through what my solution looks like. So this is just one solution, lots of different ways to do it. If your solution works just fine, great, use yours. No obligation to use mine. So over on the right hand side, we see part of my code. And what you'll see is I've got the standard header that says start Python 3. I've got a doc string from my module. I have some imports. This type ignore over here on the far right is a way for me to tell the type checker not to try to type check down into these libraries because they're not type annotated. I don't have to do that for debug and sys because they are type annotated. But I don't want to get a bunch of error messages from it on that, so I tell it just ignore those. You don't have to type your code. I like doing it because I like having the compiler tell me when I've done something wrong, but you don't have to do that. Python was developed without all this type hinting stuff. This is all fairly new. So there's my main function. How does it get executed? Well, that's the job of this thing down here at the bottom. If name is equal to main, then run main. So as a script, we'd come into this, we would execute these lines, we would execute this line to define a function, and then we execute this line, which caused us to execute the function we defined above. So my main function returns an int, but I'm going to return the return value to you. And it has a doc string, and I check to see if we have one command line argument, right? And as we know, 1 is 2 when you're doing this because the first one is the name of the program. So I check to be sure that it's 2, name of the program, and the command line argument I want. If it's not, I say you're missing the command line argument. That's maybe not right. If you gave me 17 arguments, I'd say the same thing. So maybe that's not exactly right, but I return 1 to indicate there's an error. Then I write out a debug line. You won't see this unless debugging is enabled. And then I return disassemble of that file name argument. So that's the basics of it. And let's go look at disassemble, which is the other part of my code. So here's my function that does all the real work. You see disassemble takes a file name, which is a string, and returns an int, which is going to be the return value. And in fact, if you look down at the bottom, you can see that I catch a bunch of exceptions, and in every case I return 1. And when I'm successful up here, I return 0. You could have used with. I bet a lot of you did. If you didn't, that's fine. You could just say file equal open. That's perfectly fine. You don't have to close it at the end because Python will still automatically close it for you when it goes out of scope, just the way that it works. But with is a common idiom, and so we'll use that. So I surround it with a try except block, so I catch the exceptions. And then I open up my file name with the R and B. R for read, B for binary. That's important. I don't want it to be read as a text file because if I'm reading it as a text file, Python will try to decode it. Remember, text isn't just text. Text is UTF-8 or UTF-16 Little Endian or UTF-16 Big Endian or UTF-32 or any of a myriad other different encodings that are out there. And I don't want any of that. I just want the bytes. So I'm going to read it as a binary. So open this up. File is the variable that the result of open gets assigned to by this with statement. If that seems odd to you, go read about with. It's kind of a nice little Python idiom. But saying file equal open blah 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 would work just as well. ELF gets to be ELF file around that file, so I wrap this raw file in an ELF file which will decode it for me and let me treat it as an ELF file. I go and get the section by name, and I get the section I get by name is .text, and I put that in text. If it's none, the file doesn't have a text section. Some files don't. Some executable files don't have a text section. It's weird, but I showed you how to make one earlier in the semester, and sometimes they don't have one. So I report it doesn't have a text section. I don't know what to do in this case, and so I return 1. Otherwise, I go on and I go and get the section address, the address of the start of the text section from the text section's header. And that's how I do that. This tells me the address of the first byte of the text section. Make sense? Think about that. Be sure it makes sense to you. I have a little debug line for it. And then I say data is text data. This is going to be an array of bytes. What's the address of the first byte in that array? ADDR. What's the index into the array of the first byte? It's 0. So what is the address of the data sub 25? Well, it's 25 plus ADDR. Be sure that makes sense to you. So then I go and make a little capstone object. I want to disassemble x86 64-bit. I get a disassembly enumerator. So notice I pass in the bytes and the address. This is so this little enumerator can fill in the address for each instruction it hands back. And it does, in fact, fill that in. So then I iterate over all the instructions. For instruction in the disassembly, print an F string, 16 hex characters wide with leading zeros. Print the inst address. This is the address of that instruction. It computed it because I gave it the base address of the data. And so it's able to fill that in. I have a couple spaces. And then I have the mnemonic and the op string, and I'm done. I print all those out, and I return 0. Let's talk about computability of liveness, because someone asked a question. They said, can you give me a real example that shows when liveness is not computable? Because it seems like it would always be computable. Sure. Let's do that. So the question here for this little C code on the right hand side here is X live after the first line of test? And the obvious answer is yeah, it's live because there's a path from here to the end that reads the value. Right? I return X. Since there's a path that returns it, that reads it, it must be live. Is it? Is that true? What does dofunc do? What if dofunc just like exits the program? It could do that, right? It's just call exits the program. In which case, I never read X. Or maybe dofunc never terminates. So either it maybe immediately terminates the whole program, or maybe it never terminates, never returns. I call dofunc and sometimes it never comes back. It maybe just doesn't halt. So in which case, is X live? All right, so that's an example of a case where, let me go back, a case where in order to figure out if X is live, I might have to figure out if this thing terminates, and we already know that's undecidable. So I've turned the liveness problem into an example of the undecidability of the termination. All right, there you go. Hopefully that makes sense to everybody and is a comforting answer to you. Let's talk about slicing. So we've talked about live variables. We've talked about tracing. We've talked about static single assignment. We're going to keep building up. Another important technique that fits in that bag is program slicing. It's just a way of simplifying a program, right? In engineering, one of the things they emphasize is you have to figure out what's important and relevant to solving the problem, and what information is not important and not relevant, and you can throw it away or ignore it. So program slicing gives you a way of doing that, of figuring out what's important to me, what do I need to know to get the answer to my question, and can I throw everything else away to make it easier to get that answer. So typically, the question you're asking is the slicing criteria. Slicing criteria is the name we give to the particular question that you're answering. And to formalize it, we usually use a particular location in a program. Remember, program locations are prior to a line executing or after the execution of a line completes. Those are the places where something is defined. During the line or in the line, that's kind of meaningless. So we have a location, and often we have a variable. Not always, but a lot of times you're going to slice on the value of a variable. Maybe in our case, a register. Sometimes the slice will be on whether or not a branch is taken. Sometimes the slice might be whether or not output is generated. Okay? But for the most part, those are all going to be cases where the answer to the question depends upon knowing the content of a register or a variable, and so we can reduce the slicing problem almost all the time to a location and a variable. All right, and so our slicing criteria will look like a pair, location and variable. And then what we'll do is we'll throw away anything that's not relevant to answering the question, what is the value of V at location L? Two typical types of, two ways we can usually go about it, two major types of slicing. Stammering, sorry. Backward slicing is what we've sort of been describing. I want to know what statements have an effect on the slicing criterion. Okay? So the value of the variable at some location, what statements affect that? I want to go back and figure that out. A forward slice, sort of just the opposite. It's the statements that are affected by the slicing criteria. So if I have a variable at a location with some value, what does that influence downstream? We're going to focus on backward slicing. Two types of that. Static slicing relies on the program's syntax without reference to the actual values of variables, not even symbolically. And dynamic slicing, where we actually talk about what may be present as a value in a variable. You may think, won't you have to talk about what's in the variable? Isn't the slicing criterion what's in the variable? And the answer is yes. Again, this distinction is very common in the literature, but you're going to have to sort of fudge it a little bit, right? Each side needs a little bit of the other in order to work. So let's go through maybe an intuitive example to try to motivate how you would do some slicing. So backwards static slicing. So static meaning we're not going to try to reference what's in the variables, and backward meaning we're going to start with some slicing criteria and work our way backward to ask what's relevant to figuring that out. So here we go. A little program over here. And our slicing criteria is the value of variable z at the end of the entire program. So what is z right after the last line executes? We want to figure that out. So we're going to work backward to identify lines of code that are relevant, that is, that can influence what the value is for z at the slice point. Certainly, certainly we want this last line. The last line sets z. That could not be more directly relevant to us. Okay, we want that line. We move back 1, and let's think for just a minute. I set z here. So z is alive because I want to know it's live because I want to know what it is. But it's overwritten here. So it's not live here. So prior to this line, I actually don't care about z anymore. I want to know what it is at the end. And what it is at the end depends entirely on what's in x and y and not what's in z prior to this line. So prior to this line, I care about x and y. And what does this line do? It sets r. I don't care about r. R is not x and r is not y. So I will throw this line away. Let's move back. Oh, I'm setting z. Don't I care about z? No, I don't care about z because z isn't live here, right? So you can set the value, that's fine. That's to stop you from doing that. But it's immediately going to be overwritten 2 lines later with x plus y. I don't care about that line. It doesn't change anything I care about. Throw it away. I go back 1 more. Y gets 2. I do care about y, right? Because the final value of z is going to be x plus y. I also care about x, and so I'll keep those. And there you go. There's my sliced program, and from that I can immediately see that z is 3. I just threw away the non-relevant lines. So let's try to formalize this into a procedure that we can repeat. Here's some code. I want to print the sum and product of the sequence of integers from 1 up to some input value. And you see, sure enough, I've got my little friend scanf over here. And I'm using lots of ints, but just go with it. So scanf's going to read something in, and we're going to pretend it does the right thing. We already know that sometimes it doesn't, but we're going to pretend here it does the right thing. And we're going to try to figure out what's going on with this program, because it doesn't work. If I run sumprod and enter 5, I would expect the sum to be 5 plus 4, which is 9, plus 3, which is 12, plus 2, which is 14, plus 1, which is 15. I expect the sum to be 15. First output is 15. Good. I expect the product to be 5 times 4, which is 20, times 3, which is 60, times 2, which is 120, times 1. I expect the product to be 120, but the product it reports is 0. Well, that didn't work. Okay, so there's a bug in this, and you've probably already figured out what the bug is because you're super smart, but bear with me. Programs that fit on slides is what we're studying here. Let's invent a slicing criteria to try to understand what went wrong. Our slicing criteria is going to be the value of p immediately prior to the printf line, because we know that p, which is the product, is wrong. It's wrong right prior to this line. So what's relevant to the value of p prior to this line? So at each line, we're going to keep track of a set of variables that we care about. We'll keep a line if it modifies the control flow or it modifies one of the variables that we care about. Okay? So, in your mind, think about this. We have a set, the set of variables we care about, the care set. And we will look at a line and we'll ask, does this modify a variable in the care set? If it does, keep the line. If it doesn't, we ask, does this line change control flow? If it does, we keep the line. And if it doesn't, we're done with it and we throw it away. Now, what about the care set? We have to keep track of that too. Well, we've already seen that happening. We're going to use the same basic approach we did with live variable analysis. Right? We care about a variable if it's an R value in a line we're keeping. So think about that for a minute. We keep a line if it either sets something we care about or it changes control flow. If it's setting something we care about and it's doing that by reading something else, well, we care about that something else. So that something else should go in the set. And the thing that's being written should go out of the set. Right? What about the control flow piece? Well, if the control flow change is reading something, we care about that something. And so it should go in the set. All right. The basic idea is throw away L values and then add R values. That's the basic idea. We do that for lines that we keep. Lines that we don't keep, we don't care about because we're not keeping them. So let's work backwards. We'll take one step back, and immediately we hit a snag. Just immediately, right? What's our set of variables we care about? P. That's it, nothing else. And now we're decrementing N, which is not a thing we care about. Decrementing N doesn't change control flow. We can't keep it, we have to throw it away. But certainly, if we look at the program, N's super important. It sets the control flow for the whole thing. What went wrong with our approach? We had it all figured out, and now it's gone all to heck. Well, here is the flow graph for the program. Over here is the printf. We wanted the value of P immediately prior to this. So we move back one, and oh, look at that. We moved back to decrementing N when in reality the line that runs immediately prior to the printf is the predicate of the loop. No. Alright, so really immediately prior to this, if we move back one, we should move back to the predicate of the while loop. So watch for that kind of thing. I want to be sure that you're aware of that. Drawing the flow graph can really help. So here we have a while n greater than 0. This is a line that controls the control flow, right? It modifies the control flow. And so we add the R values of this line to the set of things we care about, which means now we care about both N and P. Okay? So now we'll keep moving back and be careful with control flow as we do. What happens immediately prior to this line? Right? We do this test, and if it's true, we do some stuff. Well, here we are. We are going to go to the bottom of the loop, and we decrement N. So N is being set. N is in the set of things we care about, so we keep this line. N is an L value, so we take it out of the set. The set is now just P. But N is also an R value, so we put it back in the set. So the set is N and P again. No change. But we keep this line. We move back one more. This line is setting P. So we keep it. P is an L value, so we take it out of the set. P and N are R values, so we put both of them in the set. So the set is N and P, no change. And we move back one more. Here we're setting S. The set of things we care about, the care set, is just N and P. S is not in there, so we don't care about this line and we throw it away. We keep moving back. Now we're at P gets 0. We care about P. P is in the set of things we care about, right? So we have to keep this line. P is an L value, so we take it out of the set. There are no R values except the literal 0. So our set is now just in. We move back one more. We're setting S. The char set only contains N. S is not in it. We throw this line away. We move back one more. We're doing a scanf. This is setting N. N is the only thing in the char set, so we keep this line. N is an L value here, so we take N out of the set. What are the R values? We don't have them. We don't know what they are. There's none. So there's nothing to put back in the set. Our set is now empty, which means we're done. Nothing else can matter because we don't have any way for it to matter. Right? The only way things get into the char set is if they are an R value on a line that we're keeping. But we'll never keep any lines because our set's empty. And so we'll never encounter a line that's modifying something in the char set. So there's no way for anything to ever get back into the set. There's no way for us to go on. We stop. Nothing else prior to this matters, and we're done. Here's what we end up with. The scanf setting P to 0, the loop multiplying P by each value of N, and then decrementing it. And there we go. This slice isn't executable. You can build executable slices, but it's hard. Here is an attempt at an executable slice. It's not going to work because in just pulling in parts of the old program, we made a mistake and pulled this in, which mentions S. And S is not defined here because we threw it away, so we have a problem. My point is that building executable slices is often a challenge in high-level languages. It's maybe less so in assembly, but it certainly is in high-level languages. So the advantage of executable slices is you can run them. They can run much faster than the original piece of code. Executing them is a really good way to get an answer to your question. You slice, and then you execute the slice. But it can be challenging to do it. All right, that was backward static slicing. I think that was hopefully moderately straightforward. Let's talk about backward dynamic slicing. So again, static slicing, don't reference the contents of variables. Dynamic slicing, we will. What does that look like? Well, we're going to add some information to the set of things we know, and then use that in order to do some slicing. And the thing we're going to add to it is we're going to say, I know the result of the scanf. The scanf is going to assign in the value 1. So, that's great. The sum should be 1. The product should be 1. Let's go ahead and make that change. If we take the original program, this one, I can get rid of this line. I assign n equal 1, or I just keep track of the fact that n is 1. N is 1 here, so I can just substitute 1 in here. 1 is greater than 0. S plus equal 1, P times equal 1. 1 gets decremented, so now it's 0, etc. If I do all of that, I wind up with this. I've symbolically executed the program with n equal 1, and it turns out this is what I have left. S gets 0, P gets 0, S plus equal 1, P plus equal 1, then do the printf and the return. That's it. Now we slice. So here's what we did. We set some variables values, in this case just 1. We fed it to the program, wrote down the program trace we got as a result of that. Loop just executed once, but it could have been, if I said n to 10, we would have had 10 copies of the loop body in here, right? We execute it and record the statements to execute. And now I'm going to slice. And our slicing criteria is the same one as before, value of P prior to the printf, which means the set of things we care about contains P and nothing else. we move back 1. P is an L value, but also an R value, right? Since P is in the char set and it's being written, we keep this line. Because it's an L value, we throw it away. And then because it's an R value, we add it back. So the char set contains P, and then we move back 1. S is not in the char set, don't care, throw it away. P is in the char set, do care. It's an L value, so remove it. Now the char set is empty. Nothing else goes in because there's no other R values to put in. So the char set is now empty, and we're done. So that's it. The slice consists of the 2 lines you see in here. P gets 0, and P gets multiplied by 1. Boom. Clearly, 0 times 1 is not 1. So our error is setting the initial P equal to 0. We should have set it equal to 1. Boom. Notice how small our dynamic slice is. It's tiny compared to the static slice. That's because we had more information available to us. Let's talk about constraint slicing. Suppose instead of saying n equal 1, I said something more general about n. So instead of executing the program on a specific value, we're going to symbolically execute it on a constraint. I don't know what n is, but maybe I know something about it. Now, this can be challenging. It can be extremely computationally hard, or it can be decidable. Quantification is one way of dealing with this, right? Using quantifiers to track these conditions. Quantifier elimination, hard. Pressburg arithmetic involves statements about integers and relationships like greater than or equal. So I should say sets of integers. I should be more precise with it, but I'm not going to be because you can read about Pressburg arithmetic yourself. But it's decidable. It's a decidable type of arithmetic. And if we use it, that's great because now we can use it as a way to propagate conditions through our program in a way that's decidable. And if you think for a minute, you're like, oh, it's decidable. But yet the whole result has to still somehow be undecidable. Something must go wrong, and that thing that goes wrong is going to be loops again. All right, so let's invent a constraint. And our constraint can be that scanf line returns an n that is greater than 1. How about that? That's reasonable. We're going to flow this constraint through the program and see what we get. And so we do that. We know at scanf n is greater than 1. The next line, n is greater than 1. The next line, n still hadn't changed, still greater than 1. Here's the while loop. We know inside the bracket here, we know a couple of things. We know that n is greater than 1 because that's what brought us here. And we know n is greater than 0 because it has to be for this loop to execute. So we have n greater than 1 and n greater than 0. Now we say s plus equal n, doesn't change n. P times equal n, doesn't change n. And then we decrement n and something funky happens. I subtract 1 from it. So if n was greater than 1, right, I would now be subtracting. How would that affect the value of n? Right? N is our initial n. So what happens to it here? So if you look over here, we might have n sub 1 greater than 1. And then for this line, we have n sub 2 equals n sub 1 minus 1. Makes sense, right? We're decrementing. We can take that minus 1 and move it over and wind up with n1 equal n2 plus 1. And thus our constraint that n at this line, right here after this executes, the new n plus 1 is greater than 1. And that's what we have. And the same thing over here for this. So this should seem pretty odd, but the math holds up and you should be able to figure that out. So there are constraints. Some of these are false, right? I went ahead and added a little predicate here. If n is less than or equal to 0, return 1. If I have told you n is greater than 1, this predicate is only going to execute if n is less than or equal to 1. So I have to have this be true for this to execute, and this be true for this to execute, and both of these are false. This tells me I can throw these lines away. They will never execute given my constraint. So that's great. I get some slicing for free with that. Down here at the bottom, you've probably already figured out that if n is greater than 1, it's definitely greater than 0. I don't need both of those. I just need the tightest of the two constraints. Right? And is like intersection. And so if I have one set that's entirely contained in another, I want the smaller of the two sets. So I can throw away redundant atoms. I do that work, and I wind up with this. And that's handy. And so now I am ready to slice. I wanted the value of p immediately prior to the printf. When I slice, I wind up with this. And it's a little more than it was before, because I fuzzed up my constraint a little more. I have a little less information. But I do a little better than I may have done otherwise. This is a program optimization technique. Suppose I write general code, and I write code that has conditions to test for bad data. And I write code that checks to be sure that data is within a defined range. And maybe I have 2 or 3 different algorithms depending upon the range at which the code is executing, and I check each data point, and then I shunt it off to one of those 3 algorithms depending upon what it is. But when I analyze my data, if I look at my data that I'm going to run through the program, I figure out that my data is always in this one category, which means I can throw away all that testing. I don't have to test for bad data because I know my data is all good. I don't have to determine which of the 3 algorithms it goes to. I know it always goes to this one. I push the constraints through. I throw away anything that violates the constraints. And in particular, I'm throwing away code that checks a condition and branches. And that's great because that saves my pipeline. And so it's possible to do just-in-time optimization of programs based on their data. All right, so we've sliced statically, we've sliced with a value, we've sliced with a constraint. Let's go and slice some assembly. Here's some assembly code. The nice thing about slicing assembly is if you start with assembly, you end up with assembly. That's great. But it limits what you can do. Remember, assembly instructions are complex little beasties that have lots of moving parts. You might be able to do better if you sliced on the semantics of the instructions. We'll talk about that next time. For now, we're just going to slice on assembly. Capstone will tell you which registers are read and which are written for an instruction. That's great. The ones that are read are basically R values. The ones that are written are basically L values. And there we go. So how do I get that information? I go to my instruction object and I invoke regs access, and that gives me back an array. And the array has a 0th entry, which are the ones that are read, and a 1 entry, which are the ones that are written. And then this is a Python list comprehension. You've seen list comprehensions most of your life, right? A set of all x such that x is greater than 10. That's basically a set comprehension. A list comprehension might be the set of everything in this array such that it's even. Set of all even numbers in this array. That's what's happening here. Access 0 and access 1 are actually themselves lists. They're lists of integers, where each integer is the name of a register. What I'd like to do is have a list of the register names instead of a list of integers. So what I do is, for each integer in this list, each integer reg in this list, I go and get the register name, and I make a new list of those register names. And this is how you do that in Python. Alright. So we could use that information to do some slicing. Here's a piece of code. Let's see what happens when we try to slice on it. I've populated the read and written columns. You'll notice that M is in here. That's a little tricky, but I went ahead and populated it. So I want to know RAX at the end. My char set is just RAX because that's what I'm going to return. So is RAX written by the last line? It is. It's in the set of things that is written. So that last line will be kept. I take RAX out of the set because it's written, and I add RSP and M to the set because they're read. Right? And then I have a new set, RSP and M. And now I ask if the previous line modifies anything I care about, and it does. It modifies RSP. And so I take RSP and I remove it, and then I add RSP and M because they're read, and my new set is RSPM. Does this next line modify anything we care about? It modifies RAX and RCX, but nothing in my char set is either one of those, so I don't care. Throw it away. I keep working my way back up, and back up, and back up, and back up. And you should be able to understand all of this. And I wind up with this. I can now look for places that are disjoint, where nothing we need is written by an instruction. That's what we were doing at the same time before, but now I can go back and do it. And I'll notice I keep this line because RSP is in my char set and it's written. And I work my way back up. I keep and discard lines, and I wind up with just those lines. And if I look at just those lines, we can see what's happening. I've incremented RAX, push RCX, push RAX, pop RCX, pop RAX. I swap these two. I'm just swapping them on the stack. The other stuff is getting in the way of me seeing that. But now that it's gone, I can tell you what RAX is that gets returned. I've swapped it with RCX. I don't care about this line at all. Right? That ends up in RCX, which doesn't get returned. So that has revealed what the program is doing. Alright, new homework that's due on 2nd November. You're going to be given an unknown program. You're going to assume that libc start main is being called, and you're going to find main. You did this before manually. Now you're going to do it with Python. So I'd like to be able to run your main.py, that's what you should call it, and give it something like ls, and it'll report the address of main, or give it something that maybe it doesn't have a main, and it'll tell me it can't locate it, because some things don't have a main. So I'm going to give you an elf executable. I want you to locate the entry point, disassemble the basic block there, and find the starting address of main. You'll find the call followed by a halt, and we assume RDI is going to hold the address of main because of the calling convention and the arguments to libc start main. We're going to compute that address. It might be an RIP relative address, or it might be absolute. And we're going to print it out. If we can't find it, we can't locate main. Some hints: don't try to parse the text of disassembly. People have done that. Don't do it. Use Capstone. Be careful. Watch for RIP relative addressing or absolute addressing. Some things actually have absolute addressing. The Python executable used to. I don't know if it still does. Assume the instructions that you want will be in the text section, but make sure you handle errors gracefully because there might not be a text section. Accumulate the block. This is my suggestion to you. Just shove all the entries, all the instructions into an array, and then walk backward through the block looking for the last load effective address or move that sets RDI. And when you find it, figure out what value RDI is being set to, and you're done. So for this all to work, you need to turn on details in your Capstone instance. So when you make that little CS object, that will have a details. You'll set it equal to true. So cs.details will be true. Watch out for prefixes on mnemonics. That happens sometimes. You've probably seen that in some disassemblies. Sometimes you have a little prefix in front of it. How do you ignore prefixes? Here is a Pythonic trick to do that. I've got an instruction and I get the mnemonic, and then I split it into words separated by white space. If there's just one word, easy, that's just one thing. But if there's a couple, I only want the last one. So I split it into an array of words that was separated by white space, and now I want the last thing in the array, and I get that by indexing it with -1. So that works if there's one thing or if there's 10 things. That will give you the last one. This is a good way to get the mnemonic that you want to check. And that's it.